Hello, everybody. Welcome to this week's ExoLife Hangout. We have a great hangout planned for you today. We're going to be talking about the commonality of life in the universe, and we've got a great panel here to discuss this topic. We're going to go into all kinds of really cool things, like if we do find it, what might it look like, and where would we find it? Would it be simple life? What even is simple life versus complex life, and all kinds of cool things like that. So I love these hangouts. They're getting better and better each time. We're getting a lot of viewerships. My technology is working, so I'm very happy with the way things are going. So we are streaming live right now. It is 7 o'clock Eastern Time and a bazillion o'clock in Europe, and it is negative bazillion o'clock in Hawaii, and we are spanning the globe in our coverage of ExoLife, extraterrestrial life in the universe, I guess. Anyway, so we've got a lot of ways you can interact with us. I've got the live chats up on both Twitch and YouTube. We're also streaming on Facebook, I hope. Kevin will probably tell me if we aren't. But, it says live. Good. Then there I am. Good.
Yeah,
all right. So we are going on Facebook. Kevin is looking at those comments as well. I just have one too many things. A lot of people already on the YouTube chat. It's good to see everybody back. I see Galaxia's here, and Swiss Milk is back, and a few others. So thank you, Uric. Thank you very much for joining us, and also for setting up that Discord stuff. And Kevin's going to talk to you about that just a little bit as well. So we got a lot of people here, and please leave questions and comments for our guests, and I will relay them to you, and so will Kevin. We're also looking at Twitter with the hashtag. What is the hashtag? ExoLife. And Kevin's looking at that as well. Okay, so let's get started. So life in the universe. Very interesting topic, something we all want to know more about. The more we look, the more we only see us. And we've had SETI here trying to tell us telling us how they are looking into the universe and trying to discover alien signals or extraterrestrial signals. We've talked last week about the Great Filter, which was one of my favorite hangout topics on what might prevent a civilization or even life from reaching a certain point in its evolution, and what might those things look like, and have we passed it yet, or or do we have yet to face it? These are all things we talked about last week, so I'd encourage you to check out the hangout on the Great Filter last week. But today, the commonality of life in the universe. Now, intuitively, we might think it's everywhere. I mean, it's kind of a numbers game, isn't it? Or is it? And that's what we're going to talk about today. I mean, you think, well, gosh, hundreds of billions of stars in our galaxy, trillions of galaxies in the universe. And we already know in our galaxy that there are 1.6 planets on average around the stars in our galaxy. So sure, of course, there must be life. Has to be. Or does it? So today we're going to talk about these things. And joining me today, I have my guest, let me get her up. There she is. This is Dr. Penelope Boston. It says on the lower third Penelope, but we're going to call her Penny. And she is the director of the Astrobiology Institute at NASA Ames. And what did you say before we started? You go into dangerous places to find cute things.
Microorganisms.
Yeah, that's right. So she's joining us here tonight. So thank you, Dr. Boston, for joining us. Also
Pleasure. Joining
me is from last week. We have Dr. Peter Ward. He's a evolutionary biologist from the University of Washington. Welcome, Peter. Welcome back. Glad to have you back again.
Thank you.
Okay, cool. All right, so let's get started. Let's talk a little bit about, I'm going to get both of your opinions on this. And Penny, I want to start with you. The commonality of life. First, well, should we do that, or should I ask you about your work? I think I'll ask you about your work first. Tell us a little bit about what you're doing, and then we're going to get your opinions on the commonality of life.
Well, when I was a kid, of course, I grew up reading science fiction, and I wanted to get in my rocket ship and go places to look for stuff with tentacles and, monsters and all that stuff. And then I found out as I got older that we didn't have such rocket ships quite yet, and that I couldn't do that. But I still was really compelled by these questions about how life makes its way in extreme conditions. And of course, we have a lot of those extreme conditions on our planet. And so that attracted me to working on the processes of microbial life, which, they dominate the planet. They have for billions of years in terms of the biogeochemistry before we got larger multicellular creatures. And so I have pursued them in a lot of different environments. And probably about 10 or 15 years into my career, I discovered that there was an entire realm of amazing biodiversity, way of making a living, unusual chemistries that was possessed by microorganisms that were living under the surface of the earth rather than on top of it. And so I focused a lot of my work on caves and then later mines and, boreholes and stuff for drilling. And that pulled me into a whole amazing realm of the crust of the planet that is colonized in many areas by organisms that are quite unlike in many important ways, the kind of life that you and I are more common with. The guys we brush off our teeth every morning, and the ones in your tummy, and the ones on your skin, and the ones that inhabit the soils where they live. So that you and I are is what lured me into those subsurface realms. And the byproduct of that is that the caves and to some extent the mines of Earth take you into a realm that you can sort of relate to even psychologically as little mini planets within our own planet. So you get a very different view of our planet when you start delving into its crust. And even though I personally don't work in the ocean crust, but I know from colleagues who do that this high degree of microbial biodiversity and interesting and unusual metabolisms, as we call them, is also showing promise of being true even in the Earth's ocean floors. So that's what snagged me to go in that direction. And when I say we work in dangerous places, we don't do that just so that we can experience the thrill of dangerousness. It's because we're really looking for organisms that are pushing their abilities up against, extreme chemical and physical conditions. And so, we have to go to places to study them and capture them and bring them back to the lab and maybe do some experiments on site so that we can actually see how they do that. So that's really the motivation. And it's taken me to a lot of really amazing places.
All right. Well, we're going to get into some of that here in just a minute. But you know what I did, folks? I got so excited about getting this hangout started. I forgot to introduce my co-host, Dr. Svetlana Berdugina. She is from the Planets Foundation, and I want to emphasize that these hangouts are a collaboration between the Planets Foundation, which are in the process of building some very cool telescopes for us to hopefully find life. That's one of its stated goals, as well as to study exoplanets and everything else, and deep astronomy. So welcome, Svetlana, and please forgive me. I was going through and I got in such a hurry. So you...
That's fine. Thank you. Thank you for introducing.
Yeah.
Well, in Planet Foundation, we do believe life must be pretty abundant. We build telescopes to find it.
That's right. Otherwise, right. You obviously you're pretty optimistic about the whole thing. So
yes.
Okay. So welcome, Svetlana, and again, thank you. So okay. Well, let me go back to what you were saying there, Penny, about the kinds of life that you were looking at. You're looking in these holes. You're looking in these tubes and all kinds of interesting places. Why there? Why not? Why? Yeah. Well, let me just stop there. Why there?
Well, when I first started working on space stuff, I think that we were pretty bummed out that we didn't find something obvious on the surface of Mars. I was still an undergraduate when the first Viking missions, landed on Mars, and we were still very early on in our understanding of what goes into habitability and what makes a place habitable. And when those first missions produced results that weren't clearly positive and frankly weren't clearly negative, it sort of muddied the waters. And it took a while to sort of think again through those issues. But as I did, and, started working on extreme microbes on this planet, it became clear to me, and we wrote a paper in the early 90s, to the effect that really, if we were going to find life on Mars, it wouldn't be on the surface, in my view, that it would be in a sequestered environment on the subsurface. It might be, a relic, really, of an earlier biosphere that might have been much more robust if it exists at all. And so that was what the motivation for actually originally going in the subsurface was. As I thought about it in later years, this has sort of been refined into a much grander scheme, which is that clearly in our solar system, we seem to have only one really conspicuous life-bearing planet that holds up a big neon sign and says, gosh, I'm inhabited by life, and that's our own home planet here. But if there's life on Mars, if there are life forms in the icy waters underneath the icy shells of some of the moons around the gas giants, these are what I'm now calling a type 2 biosphere, which is a cryptic biosphere, where there's very little leakage of material to the surface. And, we don't truthfully know whether such biospheres can actually exist. But I think that that's the best chance for finding life in our solar system. So that's what drew me to the subsurface. Now, obviously, we are blessed by living
I'm sorry, I just want to clarify. You think the best chance we have of finding life in the solar system is in what you're calling this type 2 biosphere, which is under the ground?
Yeah, or under the ice.
Under the ice.
At least in our solar system. Now, that's obviously different for the kinds of astronomical work that people are doing in our community, looking for examples of the type 1 biosphere that Earth represents. That is, where there are clear chemical and perhaps even thermal signals of a very planet-dominating biosphere like we have here on Earth.
Well, okay.
And so those are the kinds of things we're looking for elsewhere. But here in our solar system, unless you can show me a planet that we haven't found yet that has that, we don't seem to have another example of that. So that's the subsurface.
So you've already, so these biospheres, go ahead and expand on this. So type 1, there's several different types of biospheres that you guys have apparently thought about, and you've named them type 1 through N. So type 1 is Earth. That's the Earth. Yeah. We're a type 1.
Insofar as the biology on Earth is very, very inextricably bound with the history of this planet. It obviously originated quite early on in the history of the planet. It has profoundly affected the geology, the oceans, all of the geochemistry atmospheres that we experience on this planet. And so it's a fundamental set of processes without which Earth would not be the way it is. So that's why it's a type 1, since we live there.
Okay.
And
then a type 2.
Yeah, it's hiding.
But that just sounds like a subset of type 1. I mean, to say Earth, we have underground
I
biospheres
think it would not
here.
Be. It would work fundamentally differently. So, for example, in our own solar system, if you look at Mars, if it is a subsurface biosphere, it has to have other energy sources besides photosynthesis. If organisms are not exposed within the photosynthetic light zone of their star, then they have to have other ways of making a living, other energy sources. And so the models for that in the work that we have done are these so-called chemolithotroph organisms.
Chemolithotroph.
Chemistry, litho means rock, and troph means eating. So these are guys who make their living
eating chemistry,
eating rock.
Chemistry, eating rock. So,
okay. Something like that. So they make their living not by grabbing photons and doing chemistry with it. They do chemistry with minerals.
Yeah, but Penny, don't we have those here? Don't we have?
Yeah,
those?
We do.
But so that's what I mean about a subset of.
Well, it's true. I mean, Earth is actually a hybrid case. Okay. But it's a hybrid case where the conspicuous dominant processes are photosynthetically driven, and they're on the surface, and you can see them.
Okay, we're going to go back to this, but I want to get to the next one. I want to get Peter in on
Sure.
this too. But go ahead. So what other kind of biospheres are there? How many?
Well,
how
I
many
don't know.
first before I ask?
I don't know.
Oh,
You know,
so
maybe
n equals question mark.
I guess
n equals X.
n equals question mark, which I provided two. Of which one we don't know if it's inhabited.
Right.
Okay.
I think maybe we can add another biosphere which we can look for on Titan, which could be on the surface but different chemistry.
Yes.
Good point.
So that's N1. I would think that I haven't given up on the idea that the big giant gas planets, we are looking at a very different kind of gaseous ocean. And, all we have is the information that we currently have about our own gas giants. But I think it's not impossible to imagine some life forms. And I certainly didn't invent this idea. Many people have written about this, not the least of which being Carl Sagan and his colleague Salpeter back in the 70s. And other people have, speculated about that, that we might have biospheres that could exist in the actual cloud oceans
Right.
that, envelop those. So that could be type 4. And, maybe there are water worlds, Neptune-sized planets that people are pointing to based on at least preliminary information from our exoplanet studies, which, so there could be a lot of different ways. I mean, the reason that I mostly divided into 1 and 2 was where was the energy coming from? So a type 1 to me is a photosynthetically driven planet, probably rocky and watery or watery. And so that's the energy source, and it's a top-down driven system. Whereas if there are biospheres in these icy moons and places like Mars, at least in the current era, they're being driven by geological sources of energy from the interior of the planet. So that is a critical zone, as they call it, the envelope of inhabited space that's essentially being driven from inside the planet out. So to me, those are two fundamental distinctions.
Okay, that's good. Okay, well, Martian colonists, which, by the way, welcome back, Guy. He has a great question that we should have started with, but we're going to get to it in a minute. But before I do, Ciro Villa. Hi, Ciro. It's good to see you again. He's got a question we can answer very quickly, and it's a good one. Where online can we find out more about the different types of biospheres as described by Dr. Boston? So is there a spot they can go to? Is there any?
Probably not. I mean, I've only written about it in the technical literature, so.
Okay.
So maybe I need to make. Yeah. You have to dig around in the literature for it.
Okay. So it sounds like this is pretty new stuff, Ciro. So I'm not sure they've got it. But so let's get to Martian colonists, and this will be a good way for me to get Peter in on this. Now, we did this a little bit last week. So we talked about this question first of all, and Peter had a pretty good answer for it, so I'm going to give it to him. But he's got a little twist on it. Can the panel define what life actually is? What do they think the best universal, in other words, non-Earth-centric definition would be for life? So, Peter, I'll give you a stab at it, and then Penny. And Svetlana, too.
Yes, and thanks, and hi, colleagues. This goes way back. Of course, Carl Sagan himself was one of the proponents for trying to define life, and NASA, the NASA Astrobiology Institute, had its own set of definitions. It circles around replication, and in no given order, metabolism, replication, but the one that I always found most interesting was evolution. And Sagan said not just evolution, but Darwinian evolution, which I thought was fascinating. And then we have many other pieces that life must be autonomous. Sometimes it got as simple as, well, you know it when you see it. The latter, I think, is not quite as
yeah,
good.
That's not a definition.
Look, it bit me.
There you go. Because in more recent times, what has become more and more fascinating, and I just alluded to this last week, is that we keep trying to define life. But on the other hand, when we're talking about life, we really need to better define death. And there's a sense that life and death are these two end members, but increasingly it looks like there's a continuum in between. And when you go to simpler and simpler creatures,
yeah,
trying
you
to
said
define...
that last week, and I'm not on board with this, but go ahead and say it in again. Yeah, about a continuum of death.
Well, some of this goes back to some of the work that's being done at the Prevention and Cancer Institute up here, where creatures are being fed quantities of hydrogen sulfide. And hydrogen sulfide puts things in essentially suspended animation. But Mark Roth is the investigator who was doing this, and he began increasingly to really question our concept of what being alive is, because you can have things that are absolutely, by that definition, dead, but they come back to life. I mean, we've got the zombie life, if you will, and simple animals really are, or not animals.
So you guys discovered zombies.
The zombie life really may be more common than our kind of life, at least in the universe, and certainly on Earth. And I say this because one of my great PhD students, David Smith, who works with Penny, for years he was studying what we called high life. And if that's high life, that kind of life is really dull, because those four things, you're talking about cells way up in the highest part of the upper atmosphere. And when they're up there, because they're being bombarded, they're not protected by the ozone. These things are getting blasted from space. And so they turn themselves into these hardy little armored creatures in a way. When they come back to Earth, they come back to life. Now, it was mentioned earlier, tardigrades, little water bears. These are little creatures that you can just take all the water out of them, and they are dead as a doornail.
Yeah, that's this thing here, which kind of freaks me out. I just showed it to you. It's being shown right now.
It's very relevant to this whole discussion.
Yeah.
And so the question is,
like a manatee.
How high on the scale of the tree of life do you have to be where life does become a binary pole with death? The life and death are only the only two end members. We humans.
So Peter, just so I can understand you, you're defining life in terms of whether it can die. So I'm still not clear on what you're calling life. Now you say there's a continuum. What something is alive? That question is more defined easier by its death. Well,
you're getting to a very interesting point. I mean, a piece of lead on a desk is not alive, but you might have to really start changing some of the words. And we started looking, what is the word between life and death? When you're talking with Roth about these continua, what is the state in between? Stasis? I don't know. I mean, there's no good English word for
hibernation. Yeah.
We got them all, but none of them seem to work right. But I think the most fascinating part, there's the tardigrade. The fascinating part is that when you're really low on the scale of things, that this whole concept of being alive is very difficult to define.
Freaky. It's freaking me out. Stop showing that, Kevin. It's like, that's
freaky. No, this is very cute one.
So
I really love it.
It looks like a manatee to me.
Yeah.
Everyone loves it.
Yes, I love it.
I have a picture of it on my desk.
I have two stuffed ones.
All right, well,
alien out of Alien.
Yeah, really. Okay, so Penny, do you want to add something to that? How do you think about life?
Well, I taught geobiology for many years. And so you have to come to grips with this question when you're teaching students. Yep. And everybody has their own laundry list of properties. So if you put any bunch of scientists in a room, and they don't have to be biologists, you can scrape up any old scientist you want. You throw them in a room and say, what's your idea of, what makes something alive or not alive? Everybody has a different list. I have a very physicsy oriented list. So for me, boundary condition is a big one. You have to have an inside and an outside of the entity.
No, that seems pretty straightforward.
Thermodynamics is a big deal. So life to me is a boundary condition entity that can essentially temporarily cheat thermodynamics by sort of exporting entropy to the outside at the expense of taking in energy and making itself more ordered on the inside. And then I think of life also from the point of view of information content. And because of the information content part of my definition, that helps me to deal with what Peter was just talking about, this fact that we, have a sliding scale of lifeiness, as one might call it. And there's stuff that's fairly clearly alive, like all of us sitting here chatting with each other. But, if you look at all the ways that living things have to temporarily shut down or slow themselves down, as long as they contain the information to revamp themselves, to get themselves started again, then to me, they're still in the lifey part of that life-death spectrum. Once they lose the ability to jumpstart their metabolism again and start living again, then they have truly died. So, getting back to our little sweet, adorable friends, the tardigrades, when they get totally dried up, and, they do this with the help of interesting sugars that they, allow to sort of dehydrate themselves with and stuff, they're not dead because their information is intact. And they can, under the right circumstances, come back to the plump, full, cute little creatures that we see and just continue on with their lives as if nothing has happened. However, if you have a tardigrade in space long enough with enough ionizing radiation, the damage from that radiation is eventually going to destroy the information content of that tardigrade to the point where it can no longer bring itself back to life. So, it's a very subtle thing in many ways. And there are lifelike processes that people have long pointed to. This classical discussion about whether crystals are alive or not. They show order, they show, various energy states, and they grow. And so they have some of those properties that we traditionally have associated with life. In my particular scheme, I think that I have an easier time figuring out that crystals are not alive in the true sense that we mean, because I do take this sort of physicsy approach. Now, the physics then enables the chemical manifestation of life processes. So you need all of the organic material that we currently have in Earth life to actually carry out this acquisition of energy and use of energy and keeping the organism ordered on the inside and all that stuff. And then the other component that Peter pointed to, which is clearly essential, and that is the property of being able to make more of yourself. So you have to make more of yourself. And the minute you have more of yourself in a universe where information transmission is bound to have flaws from that process from one organism to its daughter organism, then you have the introduction of error and change. And once you have a system with error and change in it, you automatically, in my view, have evolution, the basics of evolution. Okay. So, you add all that stuff up, and I would look at it and go, yeah, it's alive. And I wouldn't care what it was made out of. I wouldn't care if it was made out of carbon like we are, floating around in a bunch of water, or on Titan, it's not going to be that. It could be some other molecule. It could be carbon. It could be silica, something even weirder. I don't know. Oops, my light went off. Something even weirder.
I remember having to do that in the office.
Mothership, please put my light on.
Yeah, those motion sensors. Yeah, I remember that.
Yeah, so, on Titan or somewhere even weirder than Titan, we could be building life out of something else. And yet all of those properties that I just pointed to me, would still need to be present in that. And so it frees me from worrying about the particulars of the chemistry in that broad scale definition.
All right. Well, I hope, Martian colonists, I hope that helps. I got to tell you, I am hearing a lot of words I never heard before, which is lifiness, the continuum of death. That sounds like a video game. So
yeah,
I'm hearing
maybe in short we can say that life is a slow death,
Yeah, life is a slow. Well, I don't think anybody can really argue with that for sure.
Very good.
Oh, bummer.
Well,
it's a summary.
All right. Well, Svetlana, I did not get a chance to ask you this, and I'm going to ask Penny. I did talk to Peter about this last week, but I think I know the answer now because based on what you just said about life, and the continuum, the lifiness, and all of this kind of stuff, it doesn't sound. I'm not getting the sense from you guys that astrobiologists are thinking this is a very discrete thing. Like I asked you before the hangout started, one question that burns in my mind is and I've asked this to a lot of people, so my audience will have seen this question, but now I want to get your answers. You've got some primordial ooze. You've got the building blocks of life. You've got everything you need for life to exist, but it's not alive. How hard, how difficult, and I think this goes directly to the question of this hangout, how easy or how hard is that step to, or even now, I guess I need to ask, is it even a step to go from not being alive to being alive? And Penny, I'd like your thoughts on that. And then I'm going to go to Svetlana.
This is, this has profound philosophical implications.
I know, that's why I ask it.
So, I could pretend that I'm giving you a science answer, and, I will, except you have to understand it's built on an article of faith, essentially, in that I believe in the power of great numerosity. So you have...
Did you say numerosity?
Numerosity.
Okay.
You've got a planet-sized laboratory. And you've got millions of years for countless gajillions of little experiments going on.
In the goop, in the soup.
In the everything.
Yeah.
In the sweet spots, in the not sweet spots, you've got interactions of different phases of matter. You've got energy gradients. You've got stuff smacking into the planet. I mean, you've got all this stuff mixing it up. You have this vast palette of places that nature can make stuff. And I think that when the conditions on a planet are those similar in those properties to what we have experienced on Earth, I think that the emergence of life processes at this very, very close to chemistry level is the chances are very, very high. The question comes, what happens to that life afterwards? Are there planets where additional complexity just never occurs? And since we have zero information about this, all of us are acting on, our notions about what that's going to be. That's why I say it's an article of faith. I believe in numerosity, so I believe that this, multifarious suite of things going on in this vast orchestra of chemistry under the right conditions over millions of years of time is going to win out. Now, how many planets out there have this magic set of conditions? I guess probably a lot. Maybe not one in every solar system that has planets. But, I can't even guess at the odds of that.
Yeah, it seems to me that the Urey-Miller experiment from many, many years ago at least showed that amino acids aren't that hard to make, the soups and stuff, right?
And in fact, we now know, 50, 60 years down the line from the original Urey-Miller experiments, that, in fact, the galaxy itself has all sorts of ways of making simple organic building blocks. Mm-hmm. So, to me, the trick is, how do you get the more complicated ones that actually give the structural and metabolic functional properties that we have in our kind of life? And I'm a great believer in minerals. I think that, the mineral and biological evolution essentially happened together. This is something that's also been pointed out by another colleague of ours, Bob Hazen, who has pointed out that this 4,500 or so minerals, distinct minerals that we've already identified on our planet, that a vast bunch of those are only here because of this interaction of life with the mineral world on our planet. And so, the early life is basically hanging out with its friends, the early minerals. And so I think that the increasing complexness that we see in the organic material didn't have to come along early on. I think you could have very simple bags of
could have already been there.
Relatively, then. Yeah, I think so. And I think that the bags of early chemicals that you could have pointed to and said, well, that's
exochemicals.
That's a lifelike bag. Okay. It's somehow figured out how to reproduce itself.
Okay, so to summarize a little bit what I think you're saying, sometimes I just say things in a different way to see if it might make it so other people are understanding as I do, or if I'm even getting it. It helps me to understand if I'm even getting the idea. But you're saying that you're taking it as an article of faith, that the sheer fact that, or the fact that evolution just tries everything, that soon all these little experiments, of which there are an infinite number going on a given primordial soup on a given planet, that though sooner or later we're going to see something come out of that.
Yeah, and that's very distinct question from when do we get complicated life? That's a whole other
I want to go to that
realm of
question
discussion.
specifically
Yeah,
in just a minute. I
Peter's
want to know what
bag.
simple life is. I get in trouble for saying things like bacteria are simple life. They're like, whoa, what are you talking about? That's not simple. So, yeah, I want to talk about that in just a minute. But let me get your thoughts, Svetlana, on that question. What do you think about this idea of that arising out of a primordial soup?
Right. I think that origin of life and definition of life are pretty much related. So we cannot maybe define it. My students also made a long list of properties which they think is life. And, we can just make it endless until we know how it actually originates. But origin of life to me looks like a little trick which we don't know. And since we don't know that trick, it looks like magic. Imagine this magic trick you show, magician shows to others, and you don't know the trick, so you think it's magic. But if you learn the trick, you think, wow, this is simple. So I'm thinking that we are going to learn that trick, and maybe watching this magic many times in other planets, and this is how we're going to learn it. It's probably not very difficult, but we didn't figure it out yet. So maybe Peter can disagree with me, but will disagree with me that maybe he thinks probably that it's difficult to create life. But I'm thinking that once we see it, once we figure it out and watch this trick many times, we will think that, oh, that's easy.
Okay, Peter, you want to add something to this? Because this speaks directly to, I think, the question of commonality. If this is easy and if it's a simple thing, I mean, Penny seems to think, just give it some time. You're going to get some life out of this whole thing. What do you think? And Svetlana, the same. So what do you think?
Well, I wrote a book called Rare Earth. It wasn't called Rare Life. It was called Rare Earth. Actually, I think the other thing that really cracks me up is when I ask students about the diversity of life. What is the diversity of life on Earth? And they go, oh, it's 20 million or 10 million. They're talking about species. The diversity of life on Earth is one. There's one kind of life on Earth. It's our DNA life. And maybe if you like viruses, maybe we could say an RA virus is 2, but it's still down to 1. But if you go back further back, there would have been a zoo. There would have been so many different kinds with DNA of different conformation, with protein
You mean back in
codes.
our own history of our own
just
planet?
think life was produced over and over and over in an almost infinite number of varieties. Some metabolize better, some reproduce better. And what we had was the great filter by natural selection, where we ended up with one type of life with the same 20 amino acids, with all of these unifying considerations that the horrible, hardcore Darwinian world of natural selection winnowed down. Secondly, I think life occurred on this planet over and over and over during the heavy bombardment and was probably just extinguished. So I just think we were a planet of life that was exterminated repeatedly in heavy bombardment. And it finally comes back.
Okay, hang on. So hang on just a second. So in this early Earth with the soups and the ooze, you're saying we probably there was a lot of life, to use your word, a continuum of life in there as well. Then of different types.
Zoo.
A zoo.
What a cool zoo.
Zoo.
The pre-Muka zoo, the pre-Last Common Ancestor zoo would have been just a fabulous movie to make.
Okay. All right, Delbert Freeman's here. I want to ask you what you think.
That could be some kind of horror movie.
Oh, no, it's not horrible at all. It would have been the most life-affirming, wonderful movie. Hosanna! Life. Okay.
Okay, before I get to the question of the simple versus complex life, I want to talk a little bit. I want to read this comment from Susan Hunter. Antarctic ice underside has slimy drips of life. Please, Enceladus, grow pretty life. That's a great comment.
I like it.
And Delbert Freeman is asking a question about Titan. At minus 179 Celsius, is there enough chemical energy to drive the necessary biological processes? You guys were talking about that. Svetlana, you were talking about Titan as well earlier.
Well, I'm not a biologist. Yeah,
Silane.
but I definitely chemical reactions take place. And, Yeah.
Peter says silanes. So, we have expectations about how fast life should go, based on really a very impoverished understanding even of our own life here. So one of the things that working in the subsurface has taught me is that everything I was trained to think as a baby microbiologist years ago, a lot of that doesn't pertain to the subsurface. So, I have some cultures of microorganisms that take years to show up. That's even here on Earth, I have some that I've been doing continuous experiments on the same guys, waiting for them to do stuff for 20 or 30 years. And, so even on our planet, there are life forms whose pace of life, because of their ecological circumstances and their availability of energy, is very, very much slower than we come to think of as normal. So nobody says you have to have, a cooking biosphere that's ripping along at the same overall productivity that we are here on Earth in order to actually have life. And of course, I hardly thought that kind of thinking up, right? And this has been speculated on over and over again in a number of different, science fiction stories and books over the last century or so, where you have life forms that are very quiescent, maybe only come to life every 10,000 years or who knows what. Planet-dominating life forms that are very slow. So I think it's premature for us to even try to apply our Earth-derived metrics to the whole rest of the galaxy. I mean, that doesn't mean that we can't use what we know to ask those questions, like the questioner just asked. But I also think that we can't rush to judgment based on this very limited, tiny slice of what biology can be that we have here. As Peter pointed out, with all its vast and fabulous complexity and diversity here, when it comes down to the rock bottom fundamentals of what's the solvent and what's dissolved in it, this is indeed an N equal 1. Some people have suggested we have a shadow biosphere. That's an interesting idea. The idea that somehow there are life forms on this planet that are so different from the dominant life that we are not seeing them. I think that's an interesting notion. Paul Davies, who is a physicist, has advanced this idea. I actually think that it probably cannot occur because I think of exactly what Peter was saying in terms of the evolutionary winnowing of early life and pre-life down to a more and more stripped down system in terms of its fundamental structure. So I think of it in information terms, as I said before. And to me, when you have a very primitive system, you've got a lot of degrees of freedom in the system. And then as evolution works its magic and things do well or don't do well, just from the information point of view, the degrees of freedom within the system become smaller and smaller in number, to the point where I think you ultimately lock in the fundamentals. And once the fundamentals are locked in, I think there is not room for a second set of different fundamentals. So I base that really on these sort of half-developed notions of theoretical considerations. That doesn't mean that we don't keep our eyes open for this, because I feel like the environments that we go into, if anybody's going to find a weird biosphere shadowing life type, it might be us. So I haven't closed my mind.
Yeah, that would be very interesting. Please look for some.
and then I would just take everything I just told you and throw it out the window and go, well, I'm obviously wrong. But that's my sense of it, is that I don't think that on a single biosphere you can have two naturally occurring, radically different, independently operating chemical bases for life systems that are separate.
Okay, well, Sean Bonilla is commenting, I think the question is silly. Presumably, is life in the universe common? There simply must be other life out there based on the size of the universe alone. Well, maybe. Okay, but that's what we're exploring right now. I mean, I don't think it's a slam dunk, really. These guys are very optimistic that I'm with here. And yet, where's life anywhere else? Now, admittedly, we've only just started looking. But, so I don't think it's a silly question at all. Let's see. Uric Mazino's asking, are they using anaerobic digestion models in any way when searching for life? Is there a need to create an expanded version for very different and extreme environments? Anyone?
Anaerobic. Well, sure. I mean, the first, 1.8 billion years or 1.6 or whatever of Earth's history was entirely anaerobic. So anaerobes are all over the place on this planet, even though the bulk conditions on the Earth's surface are now oxygen containing. But, I could come over, if you guys were all in the same place physically, I could swab your shoes, and in culture I could bring up all sorts of strict anaerobes. It's because their anaerobic requirements can be maintained on a, crumb of soil. These guys are super tiny. They manipulate their environment in their immediate vicinity. So they can produce compounds that they exude to their environment to tie up oxygen if they don't like it. So, the anaerobic condition is the mother condition of our planet. And it's only when we started getting smart little cyanobacteria, and then later, of course, we've been endowed by all these glorious land plants that live on our planet. They completely revolutionized the composition of the atmosphere. There may be biospheres out there where that oxygen-producing photosynthesis never got invented, for all we know, in which case those would be permanently anaerobic environments.
Okay. Martian colonists had commented, I'm sorry I lost your comment, but can we, something about defining life as basically anti-entropy machines. Would that be a pretty good way to...
Yeah.
I would agree with this.
Yeah, Edmund Schroeder said that
one of those I like.
Okay. Yeah, I'm sorry if I messed up your question, but I can't see it right now in the chat.
Negative entropy.
Yeah. I mean, life loses out to thermodynamics in the end, and that's death. That's real death, Peter.
That's not no continuum death. That's
that's when you have no chance to keep shoving the entropy out the door.
Yeah. I'm going to wear all black next time. If there is next time, I'm deaf. Maybe you never know.
You never know.
You never know.
Okay, so Ciro, you had a question on for Dr. Boston about the her work on extremophiles, and what did your work, Dr. Boston, on extremophiles do for your theories on what is possible for alien life?
Well, yeah, that's a good question. I mean, it's really been the raison d'etre behind everything that I've done, and that is look for environments where there was little interference from higher life forms. So this is what has driven me to these very chemically and thermally extreme environments, because that minimizes the role of organisms that are eukaryotic and certainly that are multicellular. Now, this is not always true. I have worked in some systems with amazing large-scale life forms. But, very often we're looking to see how these organisms can make their living under these extreme conditions. And we're not, of course, claiming that the precise condition sets that we find in different subsurface environments are immediately sort of directly cut and paste, applicable to other planets. We don't know that. But what we're trying to do is map out what can the organisms do when presented with extremely high temperatures. Okay. What can the organisms do when they're wandering around in extremely acidic conditions or very high metal containing conditions? And so trying to piece the fundamentals of, gosh, how do these guys actually do that? How do they not cook their proteins in their DNA? How do they get enough energy by chewing their way through bedrock? How do they escape being buried in their own poo, basically? If you're a mineral-eating organism and you're taking one form of iron and you're transforming it and getting a little quantum of energy out of that transformation, you're building up a whole lot of that other mineral. So, how do you live with that? And so we're asking these fundamental questions that we see displayed in these natural systems. Now, if we were all knowing, I guess we could sit around and just ask those questions in our office. But nature is much wiser than we are and far more imaginative. And she's had a much longer time to work on this than any of us have. And so, I always appeal to nature to really see the examples. And then we bring those out as gems of illustration and then take those and try to tease out what are the individual components out of that. So it's taught me that I know very little. That's the overall message. That as creative as I think I am, that, nature is far smarter. And that organisms, through the processes, the amazing processes of evolution and survival and rising to the occasion to deal with environmental challenges, have invented all sorts of just stunning ways to manipulate physics for their own benefit, and also chemistry. And so, our rather crude still understanding of physics at the realm at which the microorganisms operate is something that's very hard to think yourself into. Because we're large creatures, we exist in an environment where we have certain intuitive ideas about how the world works based on our own experience. But if you actually think about the life of a microbe, these guys are so small, they're being smacked around by Brownian motion. When they're swimming through ordinary water, it's like us swimming through molasses, right? I mean,
they have a rough time.
They have a rough time,
yeah.
And yet they persisted,
Poor
and they
guys.
control the planet. I mean, you got to admire these guys, and they're cute as bugs. Anyway.
Yeah, and some of them become resistant to antibiotics, which really scares
They
me.
do, because they're so smart, and they can eat asphalt and plastic, and
Okay,
all these clever things.
Michael Jobin's got a good question, and I'm going to expand on it after you answer this. But which of you, Michael Jobin is asking, who wants to be the first one to find life out there, and why?
Everybody.
And why? You got to just say why.
Everybody.
I do too, because I'll be famous. No, that's not why. Why do you want to be the? Why do you want to find it?
I'm not so sure that I personally care whether I personally find it. I want somebody to find it while I'm still alive. Damn it.
Fair enough.
Exactly.
Mic drop, right?
That's true.
I've done my time. I've paid my dues.
You've gone through the
see
caves.
this.
That's right. Damn it. All right.
Yeah.
Good.
If you ask me where I think it's going to be found first.
Well, that was my expansion. Yes.
Yeah. Okay. So in our solar system, I think it's a real tough nut to crack because of this type 1, type 2 biosphere that I talked about earlier. I think that our exoplanet hunting friends may have the edge insofar as they've got, an increasingly large population of objects to interrogate. And even though they're going to only be able to see real obvious biospheres, our abilities to see with ever more fabulous telescopes that are, like James Webb is about to be launched, soon, and there's a whole bunch of others in the pipeline. So if I were going to bet my money on it, I would say that our exoplanet friends will probably beat those of us in the solar system.
Okay,
doesn't mean we aren't going to try.
Right. Well, Martian Colonist is talking about this in the chat, and he mentions that. So even if JWST sees no life, that doesn't tell us that life is necessarily rare. We could have just chosen bad targets. So let's talk about that for a minute. How will telescopes like JWST and those that follow it, WFIRST, and these other space telescopes, and even the European Large Telescope, ground-based telescopes from SETI, how will they detect life? Who wants to talk about that?
Well, can I make one quick caveat before we get there?
Sure. I mean, caveat away.
Yeah, well, if we find fossils on Mars, does that qualify as we have found life?
No, because it's not alive. It's just evidence.
No, it doesn't matter. It was alive.
Yeah, but you're back on your continuum of death.
I would qualify it, yes. It was
I think it qualifies.
Second life.
I'd be opening the champagne. I'd be opening the champagne.
Absolutely.
Yes.
And so this is where we really extend the possibilities. If we start pouring.
Okay, but let's say you find your fossil. How are you going to know that it came straight from Mars exclusively and what didn't come here from Earth?
Well, if it's something that radically different than anything we can find on Earth, then there's a very good possibility. I mean, the whole structural aspect is going to give us.
Abundant.
I don't think a fossil by itself is going to be enough. I think.
You can get a lot of organics out of fossils. You'd be very surprised.
Well, okay, sure. I mean, I'm not going to be poo-poo. First of all, I'm going to be like upset because I don't want to find life in our own solar system in two different planets because we've got a great filter ahead of us then. But but okay, so you found your continuum of death on Mars. That's going to be it. What else? What else? I'm trying to get you guys to talk about how JWST is going to look at gases in the atmospheres.
Yeah, exoplanets are going to have atmospheres.
Yeah, so what kind of gas does life give off that we're going to be looking for?
To me, the only thing that would be real clincher is if you've got chemically short lifetime gases, especially when you have a bunch of them, and a lot of them are chemically incompatible with each other. And that shows that you have to have very short-acting processes, spewing those out into the environment on a continuous basis.
Methane.
Yeah, methane, ammonia, carbon dioxide, and oxygen, and a bunch of sulfur gases and other forms of nitrogen gases. This complexity that we see in Earth's atmosphere is the beautiful vaporous envelope of what life is doing in the aggregate, with chemical reactions going on in all different directions. Just seeing a very simple spectrum of free oxygen in the atmosphere of a planet is not going to convince me at all, because there are about half a dozen other schemes that are non-biological that people have dreamed up that might explain that, in certain planetary circumstances. So I think, to me, it's the complexity of gases that are, easily broken down in the chemistry of that atmosphere, that are sensitive to electromagnetic wavelengths from their star and things like that. That's why I say it's got to be a really cooking biosphere. It's got to be really active. It's got to have high productivity, and it's got to be spewing all that stuff out.
Okay, well...
Yeah, I want to comment here quickly. It's quite interesting that this is what we talk about exoplanets, about non-equilibrium atmospheres and chemical compositions. But now let's apply this definition to solar system. Where do we see that? Only on Earth. So if we apply that to solar system, we can conclude there is no life anywhere else in the solar system. So that means we have to expand on this definition to be more broadly thinking, to search in the solar system and also on other planets. So if we don't, and again, like Tony said, that if we don't find some specific properties, doesn't mean there is no life. It's just like there is a saying that if the absence of evidence doesn't mean that the evidence of absence. So
yeah,
exactly. That was Martian colonists who said that, but yes.
My only caveat there is that I actually believe, if you look at our own solar system, we have a lot more potential for these cryptic type 2 biospheres than we have type 1 biosphere. Yep. So it could be that
different searches, definitely.
But off the top of my head, telescopic methods for looking for caves.
That's on the atmosphere.
It's not going there.
Absolutely, yeah. We cannot dig with telescope underground. That's for sure.
That's right. So in terms of what we can actually see telescopically, there's that realm of atmospheres, and then there's if it's intelligent, are they leaving techno signatures, right? So there's a whole other
right.
We talked about that a bit last week and the week before from SETI. So there's some talk about Sarah Seeger doing some work in the atmospheres of exoplanets, what kind of gases. We've had Sarah on several hangouts, so you should check out the list, not in this hangout series, but I've had her on past hangouts before. She's doing a lot of great work in studying the atmospheres of exoplanets, so definitely check it out. She's also involved in the TESS satellite going up. And Alex Despland, Paul, let's see. Alex Despland is commenting, Martian colonists, you should get yourself one of these hangouts someday. Or maybe join mine. Maybe join my hangout. I got one right here. Come on to hangout. You're more than welcome. I'll be happy to invite you. Give me some way to invite you, and I will. It sounds like you're doing a lot of work in this area, and you'd be an interesting person to talk to. So, yeah, definitely. Marcelo Suplicy. Why do I do this job when I'm so terrible with names? Dr. Boston already mentioned silica as another likely candidate for life forms. Any other substance that might be a likely candidate for life anchoring? Question mark. Is abundance the main factor? Question mark.
I think abundance is a big deal. We got carbon all over the place. It's something that stars produce a lot. And we got a whole lot of silica.
And also water. Lots of water in the space,
sure.
Yes.
But, people have also speculated about liquid hydrocarbons and how they would be as a life solvent, with regard to Titan, for example. Right. It would be a lot of differences in the processes of life. But basically, I think, maybe you could make it work. We know quite a bit about Silane Chemistry, which are these silica analogs of organic carbon chemistry, because they're very useful in industrial processes. Mm-hmm. However, they're soluble in organic solvents, not water, to the same extent. So that means that you could possibly build things out of them. The reason silica is such a hot property is you can stick 4 things on it, and you can make boxes. When you can make little boxes, you can make structure. And you can probably make 3-dimensional stereochemical functionality like we see with organic carbon enzymes. So that's why they've been popular. There are a bunch of problems, and that is that our system of life takes advantage of the fact that we have solids, liquids, gases, gels, all of those phases of matter that we have accessible with our chemistry. With the silane system, there are very few options for gas phase transport of materials into and out of the organism. And so people have talked about the fact that you would basically be having to get rid of your waste products in a solid form. We have what are known as iron-respiring microorganisms here on Earth. So it's not like that's totally unheard of, but it would be a very different kind of life. And at this point, we have only speculation, although I like to think about it a lot, about how we would even recognize such life if we ever stumbled upon it in one of our planetary missions.
Okay, so Delu is asking, isn't water one of the most common ingredients of the universe? And if so, doesn't it make life just as common?
Water is wonderful, and our solar system has a bunch of it, and it does appear to be pretty common in our galaxy. So I think water abundance is not the limitation, but the water distribution within any given solar system is going to be a big deal. Because if all the water of a particular solar system, because of quirky characteristics, idiosyncrasies in the formation of a particular system, is shoved to only the outer planets and is always in the solid form, then that seems to me less nurturing an environment for being a life-bearing solar system than if you have plenty of water in the liquid phase in inner planets. So I think distribution is important.
Yeah, it's a liquid phase which is important, and on the surface you need the atmosphere to have the liquid water on the surface. You need an atmosphere.
Yeah, that's why you're always hearing NASA, have a hernia every time they find planets in a habitable zone. It's a big deal. It's exciting because liquid water can be present. So yeah,
we're in a perpetual state of hernia here.
Yeah, herniated water. Okay, so Kevin, let me check in with you. Any Twitter stuff or Facebook or anything?
Yeah, I was just going to ask the question Marcelo already asked. I was just going to point that out, but
okay,
think that's about it. We're good to go.
Okay, all right. So it looks like I wanted to get to the topic of simple versus complex life, and it's already like 8:05. So we've already
next week. Let's do it next week.
Next week.
Well, next week we have it planned out, but maybe the week after we could do this again. That's just Kevin. What the heck? These things just keep going. So,
I know.
All right, folks. Well, I want to thank you all. I'm going to have to cut it here because I want to respect my guest time. Thank you very much for spending some time with us. It's been a great hangout. I want to. it looks like I want to also thank my moderators on YouTube. It looks like we got bombed with some flat earthers. So thank you for protecting us on that. They've come back. It's a periodic thing. Sometimes they go away and then they come back. So I'm glad I have you as moderators. Thank you in particular, John Suffel, for taking that time to do that. I appreciate it. I know it's late where you are. So, all right. Well, guys, that is it for this week. We didn't get to half the stuff we're going to talk to. We're going to revisit this. Any chance you guys might want to come back, maybe?
Sure, happy to do it.
Oh, thank you,
I'm
Penny.
good.
And okay, cool. So thank you,
Great.
Peter.
Yeah.
And of course,
Thank you.
Svetlana,
Thank you, Penny. Thank you, Peter.
Yeah.
And moderator, let us thank our moderator again.
Yay.
Yeah.
Thank you guys very much. All right, join us
Okay.
next week on Wednesday, 7 p.m. Eastern Time, where we are going to be talking with Dr. Robert Zubrin about stuff, right? I mean, you want to talk about it, Kevin?
Yeah, we're going to be talking about how to colonize Mars and all of the details that is in that guy's brain. So really, really excited to have him on next week.
Yeah, very excited. So join us next week. This time, if you can't catch it live, then you can watch it on demand. We're going to be streaming on Deep Astronomy channels on Facebook, YouTube, and Twitch. So definitely check it out. On behalf of my guest, Dr. Penelope Boston, or Penny Boston, she's the director of the Astrobiology Institute at NASA Ames. Also, Dr. Peter Ward, evolutionary biologist at the University of Washington. They're going to come back. We're going to finish. We're going to pick up where we left off. We're going to talk about the complex life versus simple life, and then we're going to get into some of the environments they might live in other exoplanets, and which exoplanets that we know about that are close might we find some of these life ideas that we're talking about. So join us in future hangouts every night, same night, except Kevin, you want me to start getting people the bug that we might on July 5th do this at a different time.
Yeah, July 5th might be an earlier time. So still to be determined on that, but we're just trying to make accommodations for one of our guests. He's in Europe, and so is Svetlana, so thank you so much for joining us. It's so late there.
Right.
But yeah, that July 5th might be a little earlier.
Okay, so we might do it a little different time on back then, but that's over a month away. So anyway, all right, folks, I want to thank you all very much for watching, and on behalf of all of my guests and Dr. Svetlana and Kevin and the Planets Foundation, we will see you guys next week. And as always, keep looking up.
Okay, bye.
Bye.
Thank you so much, everyone, for joining.
Thank you.
Peter, thank you so much.